Right, so we're back again, and now we're going to look at another way of looking at Debye shielding, right? So, as before, consider a neutral background plasma, right? Neutral at large scales, that's what we mean. Now, this is a one-dimensional treatment, okay? So what we do is you don't need to be too serious about this word ion. You can think of this as an ion proton. Okay, ions are protons, some positive charge. Okay, now so what you have is this is just a one-dimensional treatment. So you have X running like this. Okay, so in between, just so this would be the origin, suppose. Okay, between X equals plus L to minus L, what we do is we change the proton density from N naught to something like 1 minus delta over N naught. Okay, where the delta is of course a small number. So this is the perturbation. Now, the question to ask is how large or small should delta be and or L be? Okay? If the plasma is to remain quasi-neutral, the electron density is unchanged. Only the proton density is changed now. So this is the question we ask. Okay, so there's slightly different notation, but this is something that, you see, I'm simply copying down the formulas from the sources I'm referring to. Starok refers to charge density with a psi, and Starok uses CGS units. So this is a exercise that you should be familiar with, and as I've said repeatedly, these are just notes. You really should be reading the original books. Okay, so this is just divergence of E equals 4 pi epsilon. The 4 pi simply comes about from the fact that Starok uses CGS units, and this is just the charge density. Okay. It can again be written as del square phi, and in one dimension del square phi is simply d square phi over dx square, and that is the 4 pi remains as it is, and this is the psi, the charge over density. The over density is delta times n naught times E. From here, if it was simply n naught, no over density. There's an over density or under density, if you will, in this case, of delta n naught. Okay, so it's as if this much charge is removed. Okay, so what is the electrostatic potential due to that? That's the question we are asking. Turns out that the solution to this is quite easy. The second derivative is constant. That means on the right hand side it goes as x squared. Okay, so for x inside L, okay, where the charge density is introduced, you remember this, right? This is minus L and this is plus L. So inside here, the solution is, and this is the only place we're really interested in, the solution is this. Okay, it's an exponential, and this x squared minus L squared simply arises from the boundary condition that phi is equal to 0, as in there's no, we evacuated only this region, and therefore only this region experiences a potential, and outside of that, there's no change in potential. There's an assumption. So that would be the boundary condition, and you can check that when you put x equals L, this gives 0. Right. So what's an assumption? Phi equals 0 outside L. This is an assumption. Outside here and there. Okay. Right. Yeah. So in other words, outside of L, the disturbance has no effect, and large-scale neutrality is maintained. Okay. This question is still relevant though. Let's think about it. Okay, outside of L, but the question is how large should L be, or how small should L be, and how large or small should delta be? That's the question. Okay. Okay. Now, at the origin, you put x equals 0. phi of 0. This is the potential at the origin. Okay. All right. Now, what do you mean by maintaining neutrality even inside the perturbed region? Or rather, maintaining quasi, no, not even inside the perturbed region. What do you mean by maintaining neutrality on large scales? Okay, so you see, you have a potential at the center, right? That's going to prevent or attract. I mean, let's take like charges. Okay, in this case, you have a negative potential. So if an electron wants to penetrate inside of inside L. Okay, let me drop the blackboard so it has to be a little clearer. And so you see, you have x, and this is 0, and this is plus L, and this is minus L. Okay. Now, suppose an electron wants to penetrate from outside of L inside here. It wants to penetrate. Okay. Obviously, because there's a negative potential right here, it will experience an opposing force. But who's giving it the velocity? Who's kicking it this way? Okay, it's simply random motion by virtue of its thermal, by virtue of the fact that the electrons have a finite temperature. These are not cold electrons. Okay, so so electrons can penetrate from outside L all the way until the origin. Let's be very specific that they need to reach the origin. Simply with the thermal speeds, the perturbation, if this is true, then the perturbation is not doing much and the plasma still remains quasi-neutral. So this would be our definition of quasi-neutrality. Okay, the plasma can still be thought of as quasi-neutral as long as the electrons are able to oppose this potential barrier, and penetrate simply by virtue of their thermal speeds. And this condition can be expressed as this: half kT. This would be the thermal, the kinetic energy simply by virtue of its the half mv square, half m vrms squared. Okay, remember vrms goes the square root of kT. There's a factor of 3/2 or whatever, but never mind that. That's just an order of unity factor. So when you have v squared, you have kT, right? And so this expresses the fact that the thermal energy dominates over the electrostatic potential energy, and plugging in for the phi naught, you get this. Okay, so now you can turn this around into a condition for delta. Yeah, so this condition can also be rewritten as delta less than, I'm clubbing together some quantities and calling it lambda d over L squared, where of course lambda d squared, again as before, is defined by this quantity. Now, what does this mean? Okay, if lambda d over L, is this a big perturbation? If 1, then delta is about 1, right? So this is a big perturbation if this is the case. Okay, if that's not the case, if lambda d is much larger than L, if L is much larger than lambda d, in that case this quantity is very small and delta is very small. Okay, so in other words, if L is much larger than lambda d, in other words, the Debye screening is very effective. Okay, outside of the Debye length, the plasma is pretty much neutral. In other words, delta is very small. The charge perturbation is very small. Okay, I would urge you to think about this, and the way I'm saying it might not gel with you, but it's all in here. It's all encapsulated here. This tells you, the condition unambiguously. And this tells you that outside of the Debye length, the same conclusion as before, the plasma is pretty much neutral. In other words, the charge imbalance is screened. However, if you're inside of one Debye length, you can expect large fluctuations in charge density. The quasi-neutrality will not be preserved, and you can expect large fluctuations. That's what this is telling you. So this is another way of looking at it, at the Debye length thing. Now there are some points to think about. Why are we only talking about mobile electrons? Well, this we have discussed. Electrons have very little inertia, therefore the electrons that we hold responsible for moving around and preserving charge neutrality. How about if the charge, in this case, we have considered only the electrostatic approximation, remember. Okay. That's why we are writing divergence of E is equal to, charge density divided by epsilon naught. Right. How about a moving test charge? Okay. How about other processes such as gravitational stratification and so on and so forth that could lead to charge separation? For instance, you put a mixture of electrons and protons in a gravitational field, right? The Coulomb attraction, of course, does bind them, but nonetheless, protons are heavier, so they'll tend to sink down, and so there can be stratification. Okay, and so there can be charge separation because of that. How does that affect Debye shielding? So these are, things you can think about. If you wish, you can get a little quantitative and put some numbers to it. Interesting things to think about. Okay, so now you see, okay, so this was another thing, and there's one good thing about doing this on the computer. In class, in physical class, I would not be able to zoom in like this. This is a figure from Boyer and Sanderson. Before, it's all nice, it's all okay to talk about, to write down these equations and everything, but before, it's very, very important. I cannot overstate the importance of having a feel for numbers. Okay, so these are the kinds of plasma. When we say plasmas, what kinds of materials or what kinds of environments are we talking about? These are the kinds of environments we're talking about. Here you have temperature on the x-axis and density on the y-axis. So these would be relatively low density material. That would be a relatively high density material. Low temperature material, high temperature material. So down here, very, very low density plasmas. You have interstellar plasma, astrophysical plasmas, interstellar plasma, solar wind. Solar wind is relatively high temperature, still very low density. Solar corona, the Earth's ionosphere. Okay, and this line is where you have lambda d equals 1 centimeter. Remember, the lambda d depends only on the temperature and the density. You see here, temperature, density. Okay, so given a particular temperature and a density, you have lambda d. So this is a line of constant lambda d. Lambda d is 1 centimeter, lambda d is 1 micrometer, even smaller lambda d. Okay, so Debye, a plasma can be considered quasi-neutral outside of, say, 1 centimeter for plasmas above this line, like that. Okay, and in here you you have the ionosphere. Here you would have material processing plasmas. You deposit material, you deposit stuff onto a target. You ionize the material that you want to deposit, and you have a target that's charged, and you sputter stuff onto the target. And so this is how material processing is done. So these are the density and temperature of those kinds of plasmas are somewhere here. Low pressure arc for welding. Low pressure, and then you also have high pressure arcs. These also, welding, when you weld stuff together, you are really creating a plasma. You're ionizing material. Okay, and this would be a glow discharge. I'm assuming this is the glow discharge in these old-fashioned tube lights, not in the CFL lamps that use. Well, even CFL lamps are old-fashioned these days. You only see LED lamps, but you know the old-fashioned tube lights. This would be you know the regime, and right. So and confinement fusion. Okay. Inertial confinement and magnetic confinement. This is the regime of fusion plasmas. This is where you know these are the kinds of plasmas you generate energy from. We hope to generate energy from, and so there are different kinds of confinement strategies, inertial confinement strategies, magnetic confinement strategies, and so this is the parameter space where occupied by those plasmas. As you can see, very different from astrophysical plasmas. Okay. And this would be degenerate plasmas, the kind of plasmas that you would find again on the opposite end of astrophysics, very close to a neutron star, for instance. Okay, right. So let's move forward. Having gotten that kind of a feel for the different kinds of plasmas in the universe, you can see, you know, the breadth of plasma physics, or the breadth over which these basic principles that we're discussing, the breadth of application. Okay, whether you're doing ionospheric plasma, whether you're doing welding, whether you're doing material science, whether you're doing lab plasmas for fusion applications, all of these, you need an understanding of basic plasma physics. Okay, right. Now, there's this thing called the plasma parameter. You see, yeah. So in our discussions of Debye shielding, we were assuming an electron quote unquote fluid of density E. Whenever you mention density, like this, right? When we wrote something like this, right? N cloud is NE raised to. Whenever you mention the word density, you're automatically assuming that there are so many particles per cubic centimeter, per cubic, whatever, you know, representative length scale you're talking about, that it's meaningful to talk about a density. Right. So we are implicitly assuming that there's an the electrons can be legitimately described as a fluid. Okay, and in fact, one of the treatments that we adopted in order to justify this explicitly assumed it to be a fluid. You ascribed a pressure and a temperature to it, and the gradient of pressure was an important factor in deriving this. Okay, so the question is, how good is this approximation? How good is the fact that you're approximating the cloud of electrons as a fluid? Now, going by our discussion of neutral kinetics versus fluids, going by a discussion of neutral fluids that we did in lecture 2, was it? Yeah, in lecture 2, right? That essentially said that in that discussion we essentially said if there are lots of particles, the number of particles in some macroscopic volume is much larger than 1, then it's okay to call it a fluid, or some kind of number density times some kind of L cubed. Okay, where L is a representative macroscopic volume. Length, I'm sorry, a representative length. Okay, if this is much larger than 1, then it's okay. In this case, it's fair to say that you have the electron density and you have the representative scale here would be the Debye length. And you cube the Debye length, okay, so you can argue you really should have a 4 pi over 3 here. That's a factor of unity. Okay, when you're doing things like this, much larger than 1, the factor of unity doesn't really matter. Okay, so if any lambda d cubed is much larger than 1, then you would say that in this context you could sort of argue that the fluid approximation, the approximation of considering the electrons as a fluid with for which a density can be legitimately ascribed is good. Turns out that this is called the plasma parameter, lambda. So, if lambda is much, much larger than 1, then it's good. You're justified in treating the electrons as a fluid. Turns out that you're justified in calling this a plasma. Okay, and we will discuss why that is, what you mean by that. So a collection of particles can legitimately, yeah, so we have not really justified this yet, but for the time being, let's go ahead. A collection of charged particles can legitimately be called a plasma as long as this plasma parameter defined by any lambda d cubed is much, much larger than 1. Turns out, yeah. So mind you, this lambda d is with respect only to the electrons. You can have, therefore, so this plasma parameter is really only the electron plasma parameter. You can have an electron plasma parameter that's different from a proton plasma parameter or any other ion species for that matter. So that's something to, yeah, think about. So you can have a Debye length for, you can have really massive ions and relatively less massive ions. Okay, so the less massive ions in a multi-species plasma, as you can imagine, you can have these complications. So you can define the Debye length for different species, not only for electrons, for different other species as well. Okay, so that here in a multi-species plasma, the protons are not the heaviest particles around, for instance. Okay, right. Why are we saying this? The thing is, the more particles there are in a Debye sphere, and what do you mean by a Debye sphere? Lambda d cubed, essentially. A sphere, whose volume is lambda d cubed, a sphere with radius lambda d. So the more particles there are in a Debye sphere, the better the central charge imbalance is screened. Okay, and therefore there are few direct collisions. And by direct collisions, I mean Coulomb collisions like this. If you have a bare charge, if you have a bare positive charge, okay, and a bare negative charge moving past it like this, okay, it will be attracted, and so its trajectory will move like this. So this would be, this kind of thing is what I would call a Coulomb collision. It's not a physical collision. So this guy is fixed and massive. It doesn't move, and the light negative charge is zipping past it, but can't simply zip past it unimpeded. Because it's a bare charge, it feels its potential and it's deflected, and this deflection is what's called the Coulomb collision. Now, if the screening is very good, and the more particles there are in a Debye sphere, if the screening is very good, the full effect of the whole point of screening is that the effect of the central of this positive charge is screened, is suppressed, right? So yeah. So you can, I mean, it's screened, and therefore these kinds of direct Coulomb collisions are far fewer. Okay, so if you have a plasma with a plasma parameter much larger than 1, which is what this statement is. When lambda is much larger than 1, there are many particles in a Debye sphere. Okay, then the central charge imbalance is screened, and there are fewer direct collisions. Right, I don't know why this is not moving now. Huh. Okay. Right. Yeah. So this brings us to our discussion of collective effects. So remember, we said a plasma in the very beginning, if you remember, we made this statement saying that a plasma is one where collective effects really matter. It's the preponderance, a plasma is characterized by collective effects. Effects are collective, collective effects will just outweighing or dominating? Dominating what? Dominating two-body ones. Okay, so the cumulative, and by collective we really mean many body effects. They far outweigh the binary things such as two-body large angle collisions such as this. This would be a large angle collision. Okay, but if this charge was very well screened, if it's a very good plasma, the collision would be the deflection would be very small, and so you have this, and the electron would barely see the full potential of this, and there would be a very slight deflection like that. Okay, so the deflection would be very small. That's what characterizes a quote unquote good plasma.